The research delves into the concept of classification strength for Polish groups, particularly focusing on non-Archimedean Polish groups involving S-infinity, the Polish group of permutations of a countably infinite set. Classification strength is defined as the ability of a Polish group G to emulate every orbit equivalence relation induced by a continuous action of another Polish group H on a Polish space, in the sense of Borel reduction. This concept is introduced to organize previous work on measuring the complexity of orbit equivalence relations for certain classes of Polish groups. The authors demonstrate that several properties, including a weakening of the disjoint amalgamation property in Fraïssé theory, a weakening of the existence of an absolute set of generating indiscernibles, and not having ordinal rank in a particular coanalytic rank function, are all equivalent to a non-Archimedean Polish group involving S-infinity. Furthermore, they show that the equivalence relation equals plus, a relatively simple benchmark equivalence relation in the theory of Borel reducibility, can only be classified by Polish groups involving S-infinity. This underscores the significance of these groups in the context of classification strength. Situated within the framework of invariant descriptive set theory, which studies definable equivalence relations and definable reductions between them, the authors consider analytic equivalence relations living on Polish spaces, with Borel functions as the definable reductions. They introduce the concept of Borel reducibility, denoted by as less than or equal to b, which allows for comparisons of the complexity of equivalence relations. The authors also discuss the notion of Jean-Reisser-Godicity, which can be used to show that an equivalence relation E does not Borel reduce to another relation F. This is achieved by demonstrating that E is generically ergodic with respect to F, which precludes the existence of a Borel reduction. Overall, the paper aims to provide an absolute notion of complexity of a given equivalence relation, invariant under Borel reducibility, and explores the role of Polish groups involving S-infinity in this context. In the context of Borel hierarchy and potential Borel complexity, this paper explores the concept of equivalence relations, building on the foundational work of HKL 98. The focus lies in the study of orbit equivalence relations and their classification by Polish groups, which enables the separation of these relations up to Borel reduction. Three key examples are examined: classifiability by countable structures, turbulence, and unpinned equivalence relations. The Friedman-Stanley jump of equality, denoted as equals plus, is a paradigmatic example of classifiability by countable structures. Defined on R omega, equals plus exhibits a natural Bernoulli shift action, making it classifiable by countable structures. Jorth's work, HJ000, and HJ002a, reveals that any orbit equivalence relation generically ergodic with respect to equals plus is also generically ergodic with respect to any action of S-infinity, a Polish group of automorphisms of a countably infinite set. This implies that the absence of a comeager orbit precludes classification by countable structures. Jorth also introduced the concept of turbulence, a dynamical property that prevents certain orbit equivalence relations from being classified by countable structures. The second example highlights further separations among orbit equivalence relations classified by countable structures. A Polish group is considered complete left invariant, CLI, if it has a complete metric that is compatible, left invariant, and generates the topology. HJ099 identified a metamathematical property of equivalence relations that prevents them from being classified by CLI Polish groups, and demonstrated that equals plus exhibits this property. This property was later explored and named unpinned in Con 08. This research contributes to the understanding of the complexity and classification of equivalence relations, providing new insights into their structure and behavior. In the context of Polish groups, a strong invariance notion is introduced, focusing on two-sided invariance, denoted as TSI. A Polish group is considered TSI if it has a compatible complete metric that satisfies specific conditions. Notably, the paper provides examples of equivalence relations classified by TSI Polish groups, including E-infinity, which is induced by the Bernoulli shift action of F2. The Z-jump of E0, denoted as E, Z, 0, is classified by a CLI Polish group but not by a TSI Polish group, due to its generic ergodicity with respect to E-infinity and meager classes. This highlights the distinct classification strengths of different Polish groups. A hierarchy of equivalence relations classified by countable structures is established, starting from those classified by non-Archimedean TSI, followed by CLI, and culminating in S-infinity. Furthermore, the paper introduces a novel hierarchy above CLI, which enables the definition of one group being stronger in classification strength than another. Specifically, for every Polish space X, the orbit equivalence relation EHX is classifiable by the stronger group. This classification strength is a key concept in understanding the relationships between Polish groups and their ability to classify equivalence relations. The paper's findings contribute to a deeper understanding of the complex relationships between Polish groups, equivalence relations, and classification strength. The exploration of these concepts has significant implications for the study of Polish groups and their role in classification theory. In the context of non-Archimedean Polish groups, a fundamental lemma by Mackey and Jorth establishes that if a group G involves H, then G has stronger classification strength than H. This has significant implications, as it implies that non-Archimedean Polish groups isomorphic to closed subgroups of S-infinity have maximal classification strength. A result by Jorth provides a metamathematical sufficient condition for a non-Archimedean Polish group to involve S-infinity. Notably, the automorphism group of the limit of any Fraïssé class satisfying disjoint amalgamation involves S-infinity. However, a comprehensive understanding of the division between Polish groups that do and do not involve S-infinity was lacking. This paper bridges this gap by identifying several seemingly unrelated properties of non-Archimedean Polish groups equivalent to involving S-infinity. The main result, Theorem 1.3, establishes that for a non-Archimedean Polish group G equals aught M, the following conditions are equivalent. G does not involve S-infinity. Every disjointifying closure operator on G is trivial. KRK, M, is finite. KRK, M, is less than omega 1. There is no indiscernible support function on M. And G does not classify equals plus. This study initiates a finer exploration of the hierarchy of Polish groups not involving S-infinity, which arises from the rank function KRK. The preliminaries section reviews basic concepts and notation from countable model theory, including the use of L to denote a countable relational language and A equals BA, to denote the existence of an automorphism pi of M satisfying pi A equals A, and pi B equals B for every B element of B. Non-Archimedean Polish groups, specifically those classified as complete left invariant, CLI, and two-sided invariant, TSI, are the primary focus of this section. A crucial fact, established by Gao, states that a non-Archimedean Polish group G, represented as aught M, is CLI if and only if M lacks non-trivial L omega 1. Omega elementary substructures are uncountable models of its Scott sentence. This property is essential for understanding the structure and behavior of such groups. The Dirichlet rank function is introduced as a means to characterize CLI groups, providing a valuable tool for analyzing their properties and potential for being CLI. Notably, the automorphism group of the linear order with order type Z** operator Z, which generates the equivalence relation E, Z, 0, is an example of a CLI but not TSI Polish group. This concept has been further explored in studies such as CC22, AL, and AP21. Model theory techniques, particularly the use of ultrahomogeneous structures, play a vital role in the study of non-Archimedean Polish groups. By adding new relations to the language, it is possible to assume that M is ultrahomogeneous, thereby leveraging model theory techniques in the analysis of the automorphism group G. This approach enables a deeper understanding of non-Archimedean Polish groups, focusing on their CLI and TSI properties, and highlights the significance of the Dirichlet rank function and the example of the automorphism group of the linear order with order type Z** operator Z. The concept of non-Archimedean Polish groups, particularly the automorphism group of Knight's model, is a central focus in this context. Notably, it does not involve S-infinity, yet it is not a clique. In contrast, Jorth's construction for a countable structure characterizing, denoted by H, has an automorphism group that involves S-infinity due to its satisfaction of disjoint amalgamation. A classic example of an automorphism group that involves S-infinity is aut q less than the automorphism group of the rational linear order. This group can be shown to involve S-infinity by partitioning Q into countably many dense subsets and defining a continuous homomorphism F from a closed subgroup H of automorphisms to S-infinity. This demonstrates the intricate nature of these groups and their relationship with S-infinity, highlighting the complexity and depth of the field. In the context of Polish groups, we define a Polish group P, which involves S-infinity, as a closed subgroup of permutations pi of a countably infinite set I. This satisfies pi delta x equals delta pi x for every x element of I, where increment is a countably infinite group acting freely on I with infinitely many increment orbits. We construct a continuous surjective homomorphism F from P to St, the Polish group of permutations of a transversal T, which is isomorphic to S-infinity. The discussion then shifts to biremeasurable homomorphisms and the orbit continuity lemma, a central concept in extracting information from the existence of such homomorphisms that don't trivialize on a comeager set. Specifically, we state lemma 2.3, attributed to Jorth and Lapini Panagiotopoulos, and provide an argument for how to recover this lemma from a similar statement in LP 18. The lemma states that given a biremeasurable homomorphism F from EGX to EHY and a countable dense subgroup G0 of G, there exists a comeager subset C subset equal X such that F is continuous on C, and satisfies certain properties related to the action of G0 on X and the continuity of F. The proof of the lemma involves constructing a comeager set C that satisfies certain conditions, and then defining C as a subset of C that satisfies the desired properties. This refined version maintains the technical accuracy and depth of the original text while condensing it into a concise form suitable for voiceover narration. In the context of generalized Fraïssé theory, a sufficient condition for the automorphism group of a structure to involve S-infinity is a weakening of the disjoint amalgamation property. To establish this, the authors first provide an overview of the Fraïssé theory of classes of finite structures, which encompasses the amalgamation property and its implications. Let F be a class of finite L structures closed under isomorphism, and precedesque denote a notion of strong substructure, satisfying transitivity, reflexivity, and additional conditions. Specifically, if A precedesque B, then A precedesque LB, and if A precedesque B and pi B equals C is an isomorphism, then pi A precedesque C. The authors present a standard proposition in the field, stating that if the pair F precedesque satisfies two conditions, the empty structure empty set is in F an empty set precedesque A for every A element of F, and the amalgamation property. Then there exists a unique, up to isomorphism, countable L structure M with specific properties. The authors then weaken the disjoint amalgamation property, introducing the concept of a disjoint amalgamation, and demonstrating how it can be relaxed to achieve the desired result. The paper includes various lemmas and proofs to support the main arguments, showcasing the technical depth and rigor of the research. This weakening of the disjoint amalgamation property is identified as a necessary and sufficient condition for the automorphism group of a structure to involve S-infinity. This section of the research paper delves into the concept of a Fraïssé IZ class, a set of finite structures in a countable relational language L, with a partial order is less than or equal to F defined on it. The class must satisfy three properties: the amalgamation property, the joint embedding property, and the hereditary property. It also introduces the notion of an ultrahomogeneous structure M, which is the limit of a Fraïssé IZ class. The paper then delves into the disjoint amalgamation property, a stronger version of the amalgamation property that requires structures to be as disjoint as possible. A key result discussed in this section is Proposition 3.2, attributed to Baldwin, Friedman, Corwin, and Laskowski, BFKL 16. This proposition states that if a Fraïssé IZ class, F, is less than or equal to F, satisfies the disjoint amalgamation property, then the automorphism group of the limit structure M, denoted as aut M, involves S infinity. This result is proved by considering a class F** operator of colored versions of structures in F, where each structure is augmented with a coloring function Ca, a right-pointing arrow omega. The class F** operator, less than or equal operator F, may not satisfy the amalgamation property, but it does when assuming the disjoint amalgamation property. This allows for the computation of the limit of F** operator, less than or equal operator F, resulting in a pair M C, where C M right-pointing arrow omega is a coloring function. The paper concludes by discussing the closed subgroup H is less than or equal to aught M of automorphisms that preserve the coloring, and its connection to S infinity. This connection is crucial for understanding the structure and properties of the limit structure M, as well as its relationship with the automorphism group aught M. The relationship between the automorphism group of a countable atomic L structure M and the class of its finite substructures is explored in this section. A key goal is to establish a connection between the automorphism group and the amalgamation property, which is essential for understanding the structure of M. The concept of pseudo-algebraic closure is introduced as a weaker form of closure than definable closure. This is defined as the set of all B in M such that B is in N for every N precedence equal L omega 1, omega M with a subset equal N. The author then reverses engineers the properties required for a notion of closure that would allow for a suitable weakening of the disjoint amalgamation property. This involves working with classes of finite structures and using the closure notion to control the level of disjointness in the amalgamation. However, the converse to proposition 3.2 is shown not to be true due to counterexamples involving finite equivalence relations and the random graph. The theory developed here parallels the theory of pseudo-algebraic closure as presented in Day 77. However, the author acknowledges that this approach may not be sufficient and that a more natural coarsening of pseudo-algebraic closure is needed. This coarsening will be defined in section 4, where the right notion of closure will be introduced. This new closure operator will include possibly more elements in the closure of any set than pseudo-algebraic closure. The focus on classes of finite substructures and the development of a suitable weakening of disjoint amalgamation are key components of this section. The author's aim is to create a theory that is as simple as possible while still capturing the essential properties of the automorphism group and its relationship to the amalgamation property. In the realm of Polish groups, we introduce closure operators and independence relations to establish a foundation for analysis. A closure operator on a set I is a function Cl, phosphorus monoiodide right-pointing arrow phosphorus monoiodide that satisfies three properties for every A, B subset equal I. 1. A subset equal Cl, A. 2. Cl, A. Subset equal Cl, B. Whenever a subset equal B, and 3. Cl, A, equals Cl, A. We consider closure operators with finite character, meaning that Cl, A, is the union of Cl, A, where A ranges over finite subsets of A. A closure operator is non-trivial if Cl, empty set, does not equal I given finite subsets B superset equals C of I. We say that B element of B, Cl, C, is minimal in B over C if for every B element of B intersection Cl, BC, Cl, C, we have B element of Cl, Beak. An independence relation is defined from a closure operator Cl on a set I for finite subsets A, B, C subset equal I. We write a CB if and only if a intersection Cl, BC, subset equals Cl, C, and B intersection Cl, AC, subset equals Cl, C. Lemma's 3.4 established three properties of the independence relation. 1. Symmetry. A, CB if and only if B, Ca2. Monotonicity. Whenever A, subset equal A, B, subset equal B, and C, superset equals C, we have a CB implies A, C, B, 3. Weak transitivity. If B element of B, Cl, C, is minimal in B over C, then A, CB if and only if both a CB and a BCB. These properties are proven using the definition of the independence relation and the properties of the closure operator. The proofs involve straightforward manipulations of the set inclusions and the application of the closure operator. The authors delve into the properties of invariant closure operators and their relationship with independence relations. A lemma is proven, demonstrating how an invariant closure operator on a set I with a group action P, arch-write-down I can be used to establish relationships between elements in I. It states that if for every A equals CA, we have a element of CL, BC, then for every A equals CA and B equals CB, we have a element of CL, BC. The concept of a disjointifying property for invariant closure operators is introduced, defined as the existence of a finite subset A of I such that A equals CA and A, CB, where A, B, and C are finite subsets of I. To verify this property, one can check the conditions stated in proposition 3.6, which provides three equivalent statements for an invariant closure operator to be disjointifying. These statements include the existence of a suitable A equals CA that is independent from CB, and the existence of a suitable A equals CA that is independent from CB. The connection between the disjointifying property and the derived independence relation is discussed. The equivalence of statements 2 and 3 in proposition 3.6 allows for a simpler verification of the disjointifying property, as it only requires checking two easier statements separately. This proposition serves as a foundation for further exploration of invariant closure operators and their applications in model theory and other areas of mathematics. This section of the research paper delves into the classification strength of Polish groups, focusing on the interplay between sets A, B, and C, along with their closures under a given preorder is less than or equal to. The primary objective is to demonstrate that if certain conditions are met, then a specific element A must be in the closure of set C. The paper commences by establishing the equivalence of four distinct statements pertaining to the classification strength of Polish groups. It subsequently proceeds to prove that statement 4 implies statement 3, which in turn implies statement 2, and finally statement 2 implies statement 1. Detailed proofs for each implication are provided. Firstly, the paper shows that statement 3 implies statement 2 through an induction argument on the size of the set B, CL, C, where CL, C, denotes the closure of C under the preorder is less than or equal to. The base case is trivial when B, CL, C, equals 0, and the induction hypothesis is utilized to find an element A that satisfies the desired properties. Next, the paper demonstrates that statement 2 implies statement 1, again employing an induction argument, this time on the size of the set A, CL, C. The base case is also straightforward when A, CL, C, equals 0, and the induction hypothesis is leveraged to construct a set A that meets the required conditions. Lastly, the paper proves that statement 4 implies statement 3. To achieve this, it introduces a new preorder is less than or equal to on the set of all A, with A equals CA, defined as A is less than or equal to A, if and only if for all B equals C flat, A, element of CL, B. Right pointing arrow A, element of CL, B. The paper then illustrates that is less than or equal to is indeed a linear preorder and that A is less than or equal to A implies A, element of CL, A, C. This leads to a contradiction under the assumption that A, E, addio, / element of CL, C, as either A is less than or equal to A, or A is less than or equal to A for every A equals CA, and thus A element of CL, C, by statement 4b. In conclusion, this section of the paper offers a comprehensive analysis of the classification strength of Polish groups, employing various mathematical tools and techniques to establish the equivalence of different statements related to this concept. We begin by demonstrating that is less than or equal to is a linear preorder, which entails proving its reflexivity, transitivity, and linearity. The first two properties are evident, so we focus on proving linearity. For contradiction, assume there exist A0, A1 equals CA and B0, B1 equals C flat with certain properties. By the second statement, we have B1 element of Cl, A1C, and thus a 0 element of Cl, A1C. This implies a 0 element of Cl, B0C, due to the first clause of the first statement, contradicting the second clause of the first statement. Next, we delve into the realm of disjointifying closure operators and their relationship with S-infinity. Specifically, we aim to prove theorem 3.7, which states that if I is a countably infinite set and P is less than or equal to S, I is closed with the natural action P clockwise top semicircle arrow I, and I has a non-trivial invariant disjointifying closure operator Cl, then P involves S-infinity. To establish this theorem, we define an L structure M living on I, where for every a, b element of I less than omega, we have that R b, M holds if and only if there exists some G element of P with G A equals B. We show that M is ultrahomogeneous, and thus if we let F be the age of M, we have that F is less than or equal to L, is a Fraïssé class. For each element of F, we have the invariant disjointifying closure operator CLA on A that it inherits as a substructure of M. We then define F as the class of pairs A, CA, where A element of F and CA, a right-pointing arrow omega union, null, satisfies certain properties. We say that A, CA, is a strong substructure of B, CB, denoted A, CA, B, CB, if certain conditions hold. We note that is a notion of strong substructure, and that F consists of the pairs A, CA, for which the empty structure, empty set, is a strong substructure. Our goal is to show that F satisfies the assumptions of proposition 3.1. The only challenging part is demonstrating that it satisfies the amalgamation property. Suppose A, CA, B, CB, C, CC, element of F satisfies certain conditions. Because CL is disjointifying, after replacing C, CC, with some C, CC, equals A, C, CC, we may find D element of F such that B is less than or equal to LD and C is less than or equal to LD and CLD, B, intersection C subset equals CLD, A, and CLD, C, intersection B subset equals CLD, A. By shrinking D, we can assume the classification strength of Polish groups, particularly the subgroup S-infinity, is a pivotal concept in the realm of mathematical structures. A well-defined and compatible coloring CD for a given substructure D is essential, as it ensures that the colorings of its substructures B and C are also well-defined and compatible. The authors demonstrate that the limit of the quotient structures, F** operator, F, is isomorphic to M, C, where M is a non-trivial structure and C is a coloring that assigns a color to every element in M. This result highlights the intricate relationship between these quotient structures and their limits. In addition, the paper introduces a subgroup H is less than or equal to P, consisting of all elements G such that there exists a permutation sigma element of S-infinity satisfying C, Ga, equals sigma C, A, for every element of I a continuous homomorphism F. H right-pointing arrow S-infinity is defined, mapping each H element of H to the unique permutation sigma element of S-infinity associated with it. To prove that F is surjective, the authors construct a sequence of finite substructures and is less than or equal to M and Bn is less than or equal to M, along with elements Gn element of P, satisfying certain properties. These constructions are then used to show that Gn right-pointing arrow G infinity for some G infinity element of P with G infinity element of H and F, G infinity, equals sigma. This demonstrates the surjectivity of F, which is crucial for establishing the classification strength of the Polish groups involving S infinity. This research provides valuable insights into the properties and behaviors of Polish groups, shedding light on their structure and potential applications in various fields of mathematics. Dirichlet's theory, as presented in DE 77, revolves around the concept of rank function and its relation to pseudo-algebraic closure. The Dirichlet rank, denoted as drk, A, B, is an ordinal value that measures the distance between an element A and being fixed by the stabilizer of B under the action of P. This rank function serves as the foundation for the Dirichlet closure operator, DCL, which assigns to each finite subset B of I the set of all A in I such that drk A, B, is finite. Theorem 4.2, attributed to Dirichlet, establishes a modeled theoretic characterization of the Dirichlet closure. For a countable relational language L and a countable L structure M with the natural action aught, M, arch right down M, an element A is in the Dirichlet closure of B if and only if A is in every elementary substructure M0 of M containing B. This theorem bridges the Dirichlet closure to the notion of elementary substructures in model theory. The proof of Theorem 4.2 employs an inductive argument on the Dirichlet rank, drk A, B. When drk A, B, is 0, any B equals BA must be equal to A, implying the element of M0. For higher ranks, the existence of a suitable C element of M ensures that a element of M0 by the induction hypothesis. This result underscores the significance of the Dirichlet rank and closure in understanding the relationship between elements and their stabilizers under group actions, as well as their connection to modeled theoretic concepts like elementary substructures. The Dirichlet closure operator and its characterization in Theorem 4.2 provide a framework for analyzing the interplay between elements, their stabilizers, and the structure of the underlying model. This framework has implications for understanding the properties of elements and their relationships within the context of model theory and group actions. The authors investigate the classification strength of Polish groups involving the symmetric group S infinity. To establish this, they first prove the backwards direction by constructing AL omega 1, omega elementary submodel M0 of M with A, epsilon adio, / element of M0. This is achieved by defining a set C, subset equal M with the closure property, asterisk operator, over C and A, epsilon adio, / element of DCL, C. The authors then construct a sequence of sets Cn, where Cn plus 1 has property, asterisk operator, over Cn, and define M0 as the union of these sets. Next, the authors prove proposition 4.3, which states that the operator DCL is a locally finite invariant closure operator. This is done by showing that DCL is locally finite and invariant, and that it satisfies the additional property that if a element of DCL, BC, for every C, equals BC, then a element of DCL, B. The authors then relate the non-existence of non-trivial L omega 1, omega elementary substructures to dynamical properties of the automorphism group, citing Gauss' 1998 result that a Polish group G is Klee if and only if there is a complete metric on G compatible with the topology, making the distance function left invariant. The authors then present Theorem 4.4, which states that a Polish group aut M is Klee if and only if there is no M0 subset equal M such that M0 precedes L omega 1, omega M. This is followed by Corollary 4.5, which lists 5 equivalent statements, including the Klee property of aut M, the non-existence of uncountable L structures satisfying the Scott sentence of M, and the properties of the DCL operator. The concept of disjointifying rank is introduced, building upon the Dirichlet rank. Given a set I with a group action P, a finite subset B of I, and an element A in I, the disjointifying rank KRK, A, B, is defined recursively. Specifically, KRK, A, B, is less than or equal to 0 if for every pi in P with pi restricted to B being the identity, pi, A, equals A. For alpha greater than 0, KRK, A, B, is less than or equal to alpha if either there exists some C such that for every C, similar to B and C, KRK, A, BC, less than alpha, or for every A, similar to B and A, either KRK, A, BA, less than alpha or KRK, A, BA, less than alpha. The disjointifying rank KRK, A, B, is defined as the least ordinal alpha such that KRK, A, B, is less than or equal to alpha or infinity if no such alpha exists. Several basic properties of the disjointifying rank are established, including the monotonicity property. For finite subsets B and C of I with C containing B, and A in I, KRK, A, C, is less than or equal to KRK, A, B. Additionally, if there exists some c in I such that krk, a, c, less than infinity for every c, similar to b and c, then krk, a, b, less than infinity. A closure operator CL-min is defined on M, where A is in CL-min, B, if and only if krk, a, b, less than infinity. The authors prove that CL-min is indeed a closure operator using induction on alpha, showing that for any finite c and a, b and I, if krk, a, c, is less than or equal to alpha and krk, b, a c, less than infinity, then krk, b, c, less than infinity. This result has significant implications for the study of group actions and their properties. The classification strength of Polish groups is examined, with a focus on the role of S-infinity. To begin, it is proven that CL-min is a disjointifying closure operator, satisfying clauses A and B from proposition 3.6. This is achieved by assuming that for every A equals CA, either krk, A, AC, less than alpha or krk, A, AC, less than alpha, and employing an inductive argument to establish the claim for all alpha. Next, it is demonstrated that CL-min is the minimum disjointifying closure operator. This is accomplished through an inductive proof on alpha, showing that if krk, A, C, is less than or equal to alpha, then an element of CL, B, for any other disjointifying closure operator CL, B. This result underscores the significance of CL-min in the context of classification strength. The concept of indiscernible support functions is subsequently introduced. These functions map finite subsets of a set I to finite subsets of omega and serve as a motivating example of a non-trivial disjointifying closure operator. Furthermore, they provide a technical tool for further analysis, facilitating the exploration of classification strength in Polish groups. In this section, we define a support function sup as a mapping from finite subsets of a set I to subsets of omega, satisfying three key properties. Firstly, for any finite subsets A and B of I with a subset of B, it holds that sup A is a subset of sup B. Secondly, sup is considered non-trivial if there exists a finite subset A of I such that sup A is not equal to the empty set. Lastly, sup is said to be indiscernible if for every finite subsets A and B of I with a subset of B, and for every finite subsets U and V of omega with sup A equal to U and sup B equal to V, and for every V similar to UV, there exists some B similar to AB with sup B equal to versus. We assume that sup is such a function and our goal is to show that CL-min is non-trivial. To achieve this, we prove lemma 5.1, which states that if A is an element of CL-min B, then sup AB is equal to sup B. The proof involves induction on alpha, where alpha is the rank of the krk function, which measures the complexity of the relationship between A and B. Given the lemma, we can conclude that if P, a subset of I, has a non-trivial indiscernible support function, then it has a non-trivial disjointifying closure operator. This is stated in proposition 5.2. The existence of such a support function is guaranteed by the fact that if sup is non-trivial, then there must exist some finite B and A such that sup B is not equal to the empty set and sup AB is not a superset of sup B. The author's primary objective is to derive an indiscernible support function from a biremeasurable homomorphism, focusing on the case where P classifies equals plus. They introduce a presentation of equals plus involving a countably infinite group increment acting on a countably infinite set J with infinitely many orbits. A transversal T for increment arch right down J is defined, and an enumeration T equals Tn, n element of omega, is fixed. The set Q is less than or equal to Sj of permutations satisfying delta pi A equals pi delta A. For every delta element of increment and element of J is defined. The authors then define Y as the G delta set of all injections F. J right pointing arrow R, which is a Polish space with the pointwise compactness topology. The natural action Q, arch right down Y is defined, and it is shown to be continuous with respect to this topology. In lemma 5.3, The authors establish that the equivalence relations EQY and equals plus are Borel bireducible. This is achieved by showing that equals plus is less than or equal to B EQY and EQY is less than or equal to B equals plus. The first direction is proven through a Borel reduction from equals plus to EQY using a Borel function G. R right pointing arrow R omega satisfying specific properties. The second direction is proven by constructing a Borel reduction from EQY to equals plus using a Borel bijection H. R increment right pointing arrow R and a function f. Y right pointing arrow R omega. The authors define N triangle left equal as the closed normal subgroup of G element of Q satisfying G a element of increment A for every element of I. The homomorphism chi. Street right pointing arrow Q is defined, and N is shown to be the normal complement of IM, chi. The countable subgroup SFINT of pi element of street with finite support is defined, and N0 is defined as the set of H element of N with finite support. The countable dense subgroup Q0 equals chi, SFINT, N0 is defined. Finally, the authors set up the context for the rest of the section, where P is less than or equal to SI is a closed subgroup with a natural action P, arch right down I, and X is a Polish space. A biremeasurable homomorphism F. Y right pointing arrow X is fixed, which will be used to derive an indiscernible support function. In this section, the author presents a proof for claim 1, which states that if both U and V support a finite subset A of I, then their intersection U intersection V also supports A. The proof begins by defining a set U that witnesses the support of A for both U and versus it then proceeds to find elements pi0, pi1, and pi2 in the stabilizer group ST, V, such that pi equals pi2 ring operator pi1 ring operator pi0, where pi0 and pi2 are involution elements with specific properties, and pi1 is constructed to satisfy the conditions of the claim. This construction ensures that the action Q, arch right down Y restricts to an action N, arch right down Y, and the homomorphism F from ENY to EPX is non-degenerate, leading to a non-trivial indiscernible support function. The authors delve into the classification strength of Polish groups involving the group S infinity, examining 4 distinct cases. In each case, they demonstrate that pi2, pi1, pi0, A, equals pi, A, utilizing the definitions of pi1, pi2, and sigma. Consequently, they establish that A, chi, pi1, H0 element of StaBQ0, V, chi, pi1, H0y equals chi, sigma, H0y element of U, and F, chi, pi1, Hy, element of stab P, A, F, Y, B, chi, pi2, H1 element of StaBQ0, U, chi, pi2, H1, chi, pi1, H0y, equals chi, sigma, chi, pi, Hy element of U, and F, chi, pi2, H1 chi, pi1, H0y, equals stab P, A, F, Y, and C, chi, pi3, element of StaBQ0, V, chi, pi3, chi, pi2, H1, chi, pi1, H0y, equals chi, pi, Hy element of U, and F, chi, pi, Hy, element of stab P, A, F, Y. The authors also introduce the concept of support of A, denoted as sup, A, which is the minimal U that supports A. They aim to prove that sup is indiscernible and demonstrate claim 2, stating that if U is a support of A witnessed by a neighborhood U0Y0, then for any finite support sigma element of street in H element of N0, and G element of P, if chi, sigma, Hy0 element of U0 and F, chi, sigma, Hy0, equals GF, Y0, then sigma minus 1U is a support of G minus 1A. The proof of claim 2 involves setting V equals sigma minus 1U and B equals G minus 1A, and showing that V is a support of B. The authors construct an open set U1Y0 such that for every Y element of U1 intersection C, chi, sigma, H Y element of U0 and F, chi, sigma, H Y, element of GSTABP, B, F, Y. They then argue that U1 witnesses that V supports B, and finally, they demonstrate that F, GVY, element of stab P, B, F, Y, for arbitrary GV element of staba Q0, V, and Y element of U1 intersection C. In the context of group actions and stabilizers, the support function, sup, is investigated, revealing its indiscernible nature as a function from set I to set J. This property is established through a series of claims that exploit the relationships between supports and stabilizers. Firstly, it is shown that for any finite A subset equal I and finite U subset equal J, if A is equivalent to U, then there exists a finite V subset equal J such that A is equivalent to versus. This result is obtained by leveraging the definitions of support and stabilizers, along with the assumption of continuous action of Q on Y. The second claim proves that if A is equivalent to both U and versus, then U is equivalent to versus. This equivalence is established by applying the previous claim and utilizing the properties of stabilizers and supports to construct a chain of equalities. The third claim demonstrates that if sup is trivial, then f, y, belongs to the equivalence class EP_XF, y, for every y, element of C. This is achieved by assuming sup's triviality and constructing a sequence of elements in Q_0 and P, which converges to a limit element in P. This limit element is then used to establish the desired property of f. Finally, it is shown that if f is a reduction, rather than just a homomorphism, then sup must be non-trivial. This result is obtained by considering the set EQ_Y, which is proven to be meager under certain conditions, leading to the desired conclusion. The non-triviality of sup is thus established, relying heavily on the definitions and properties of supports, stabilizers, and group actions, as well as careful constructions of sequences and limits within these structures. This study concludes the series on classification strength of Polish groups by examining the case involving S infinity. A countable set I and a closed subgroup P is less than or equal to Si are considered, where P has a non-trivial indiscernible support function. The main theorem establishes that P, arch-right down I classifies equals plus and is not generically ergodic with respect to EPX for some Polish space X. The theorem's equivalences are proven, revealing a connection between indiscernible support functions, classification of equals plus, and generic ergodicity. Specifically, the equivalences demonstrate that the existence of a non-trivial indiscernible support function for P is equivalent to P, arch-right down I classifying equals plus and not being generically ergodic with respect to EPX. The study provides a comprehensive list of equivalences, which are crucial in understanding the relationship between indiscernible support functions and classification strength. These equivalences are instrumental in establishing the main theorem and have significant implications for the study of Polish groups. The research contributes to the understanding of the interplay between indiscernible support functions, classification of equals plus, and generic ergodicity. The findings have important implications for the study of Polish groups and their applications in various fields. The study's results also highlight the significance of indiscernible support functions in understanding the classification strength of Polish groups. The study's methodology involves a combination of model theoretic and topological techniques, which are used to establish the equivalences and prove the main theorem. The research assumes a basic understanding of model theory and Polish groups, and the results are presented in a rigorous and formal manner. The study's limitations include the assumption of a countable set I and a closed subgroup P is less than or equal to Si. Future work may involve extending the results to more general cases and exploring the implications of the study's findings in various applications.